something like this, yeah.
Working first as a leader of homing grant, and then with Professor Horodecki in his map, Michał Horodecki. And today, and of course after this, he returned to Warsaw in October, and he's now the leader of the quantum computing group in our center, in the Grand TeamNet. And today he will tell us about quantum computational supremacy, a beginner's guide.
Thank you, Adam, for this kind introduction. It's great to be here to present something here after well, quite a few years of being away, and it's great to be back in CTP. So, yeah, the idea of this talk is to give you a very gentle introduction to this idea of quantum supremacy, and along the way I will introduce some basic concepts of related to quantum computation. But let me maybe start with debunking a bit. Oh, actually, I see that. Cool. With debunking a bit the quantum computing hype that maybe many of you saw in the media. So of course we have very nice progress in recent years. So sizes of controllable quantum systems increase, quality of gates improves. Important technological giants like Google, IBM, Intel, Alibaba, many others, they invest a lot in this technology. But in the popular coverage, somehow the expectations are put like a bit too high, because still we're far away from like scalable quantum computers. They are not, and even if we were there, they would be not all powerful. I just wanted, just as entertainment, share with you some a bit like exaggerated claims. Okay, I mean this one. Okay, some tweet by Financial Times. Okay, says that it has to do with this with this Google demonstration of supremacy. So it says that Google can carry out computations that are beyond ability of the most powerful supercomputers today. Strictly speaking, as you'll maybe what you'll get from my talk, it's like what they do, it's not exactly computations in the sense that we understand. Okay, so I think it's like a bit overhyped. Another claim, it's about some other paper. So you know, there is this idea of short algorithm that in principle can break cryptographic systems, and there was some advancement in regarding practical implementation of this algorithm, but on the theoretical side. And then you have such a tweet that, you know, suggests that it's just next door, it's just tomorrow, it's going to happen. But I think it won't. Just some other, I mean, this is like crazy a bit. I don't want to comment. Okay, travel in time. Lastly, okay, this is actually quite interesting, and it also has to do with our quantum advantage, quantum supremacy topic today. So it enters politics, okay? So daughter of president of US actually sort of tweeted after the Google announced the results that it's a success. And just one more comment. The same day that Google announced their results, or they appeared actually in Nature. The same day on Archive, the Chinese group that does boson sampling, this is another paradigm for quantum advantage. They put their paper sort of improving also the quality of those experiments. So it becomes a bit of like an arms race these days. Okay, so okay, just that's outline of the rest of my talk. So yeah, I'd like to maybe give you some basic understanding of of this recent quantum advantage, quantum supremacy demonstration by collaboration between Google, University of Santa Barbara, and NASA. And I won't be talking exclusively about this experiment. First, so that we are all on the same page, I'll give you some basics and context in quantum computation. Then I will introduce this paradigm of quantum computational advantage. Then that will be actually the kind of yeah, for me challenging part, because it's not my work really. So I try to explain what basically this Google team did. And lastly, I will comment about the relevance of classical simulation of complicated quantum devices, especially in the context of like some controversy. I mean controversy. IBM announced basically the same day that Google published a paper that they can actually simulate those systems pretty well, like not in 10,000 years. Okay, I just comment on this later. Okay, so just just introduction: classical versus quantum computation. So classically, we store information in bits. So just some number, either 0 or 1. And quantumly, we have qubits, right? So probably most of you heard about qubits, but let me just reiterate. So we have still 0 and 1, but we can have like continuous spectrum of like superposition of all possible states. Okay, and they like formally form like a block ball, those pure states. Right. And now interesting things start to happen when we have compound systems. So when we have n bits, it's just like bit string like of length n. Okay, so this is how we store information in computers. But now when we have n qubits, by the virtue of this principle of quantum superposition, okay, we still have those basis states that are associated to bit strings, but we have like exponentially many complex amplitudes that appear there. Okay, and the state of the system lives in this exponential Hilbert space, which is tensor product of many single particle Hilbert spaces. Great. Now, how computation is done on the classical level? So you just apply logical gates, that is, let's say, deterministic transformations of bit strings. So we have some basic gates like and, or, not, Toffoli, etc. So they just transform our bit strings, and then we are going to get the outcome in the end of the computation somehow. On the quantum level, we don't have logical gates, but we have unitary transformations. So general unitary transformations that, according to the rules of quantum mechanics, like rule the evolution of the system. Okay, so the wave function is transformed by the action of this unitary. Okay, but both in classical computing and in quantum computing, we cannot like apply arbitrary complex gates for free. So we are, let's say, forced to work to build our circuits from primitive blocks. Okay, so from logical gates that act on, let's say, small number of non-trivially on small number of bits. So this is some technical name, fan in, it should be fan out. So like they take two bits, they split up 2 bits. Okay, the I don't know which gate would be like here. I don't know those gates. Like when you take them together, let's say that they have this property, for example. And on the quantum level, we have, let's say, spatially local unitaries. So unitaries that act non-trivially on just, let's say, 2 particles, okay, on your system. So just in this graph, so here we have like 2 qubit unitary. Okay, here's 2 qubit, here it's like 3 qubit. Okay, so we can build our general circuits from those primitive gates. We cannot, in one shot, implement everything. Okay, So now, another important difference has to do with readout. So in classical computers, readout is trivial. So we just read out the values of bits that are stored in our memory. But quantumly, like when we have such a superposition of states, we are going to get, according to the Born rule, different outcomes, like with probabilities given by the moduli squares of the amplitudes that we have there. So quantum computers are intrinsically probabilistic. Good. So these are just so that we are on the same page. So by the way, if you have any questions, please feel free to interrupt. Okay. And now just a bit. Okay. Okay. Another humorous figure. Yeah. So just I don't want to go that much into details, but there are different, let's say, resources or features of quantum mechanics that people think can be responsible for speed up in computation. So one of them is this principle of superposition. So in some sense, quantum systems can be in different states at the same time. Okay, it's just some popular exposition of the superposition principle. Another feature is entanglement. So when we have these complicated systems, states they don't need to factorize into factors in the respective tensor products. Okay, so we call such states entangled, and that's also one of the, let's say, features that people associate to like quantum speed up, right? And some important caveats. So that I would then comment on later. So we have non-cloning theorem in quantum mechanics. So we cannot. So this is an important difference from classical computing. We cannot proliferate a known quantum state. We cannot create many copies just like for free. It's forbidden by the rules of quantum mechanics. Again, we have this probabilistic readout. Classically, we have deterministic readout, and lastly, we have huge complexity associated to manipulation of large quantum systems, because Hilbert space is huge, and we do have accumulation of errors in such large, complicated devices. So speaking about errors, I just want to, okay, it will be just some popular exposition, maybe explaining why we don't have yet fully large quantum computers working. So you know, so like when we have errors in quantum computers, so first of all, we cannot duplicate our functions, so we cannot trivially correct the errors that occur there. Okay, so classically we will just copy the bits. We cannot do it in the quantum realm. Also, quantumly we can have different errors that affect our qubits. Okay, so we can have the standard, let's say, X error that flips 0 and 1. Okay, but we can also have so-called phase flip, the Z. Okay, that would introduce the sign here, and Y, which is like compose like X and Z in some sense. Okay. Yeah.
Time evolution, and
yeah.
time evolution is unitary. What
yes.
an error?
Sure. No. So so this is sure. So you need to take into account the fact that quantum systems are not isolated; they interact with environment, and then you have some quantum channel that describes this. Yeah. Yes, yes. Yes, and in some regimes, let's say these are the errors that, I mean, okay, for a single qubit, these are more or less like all the combinations of such errors, this is all you can get, okay? And then, so it's not only more difficult to correct for the errors because of non-cloning theorem, it's you also have more errors. Yep. Yeah, but this is what I said, that effectively you can simulate all the others by somehow combinations on a single qubit. But yeah. Still, there is this remarkable result called threshold theorem that tells you that if this is in the simplified model where you assume IID noise affecting every qubit individually, okay? If the probability of occurrence of a single error is low enough, below some threshold, then in principle one can do error correction. So one can compose bigger and bigger like encodings of logical information into a large quantum system, and then on the with this like the error in the further and further logical steps would decrease. So just in principle error correction is possible. Okay. Yeah, just some exposition of the state of the art. But still, the overhead that we have at the moment is large. So to do some useful computation, you need to put at least 1,000 physical qubits to encode one logical qubit. Okay, so this is like roughly state of the art. I think it's quite okay. I'm not following this super exactly. So this is in a even more simplified. So this is something that you would need to compute to implement Shor with, I don't know, 10,000 bits or something like this. Okay. So this is on the this is in this particular model which strips away, let's say, the physics a bit. Okay. Yeah. Yes. Yes. Okay. Yeah. Yeah, but this is maybe, okay, this is for a single qubit. So then you need to have many logical qubits. You need to also have some ancillas. Yeah. Yeah. I mean, the exact number, they don't match. They don't matter that much for me at the moment, but the take-home message is that we are far away from this at the moment. Okay, so now I can give you some background on like what are the paradigms in which people are, expect to get let's say quantum speed up. Okay, so one is rigorous, I call it rigorous quantum algorithms. I will be describing each of those things in detail, especially this quantum computational advantage or supremacy. So rigorous quantum algorithms, heuristic quantum algorithms, quantum simulators, and lastly this quantum computational advantage or supremacy. So just rigorous quantum algorithms. So there are some primitives, some algorithms that show advantage compared to the best known classical algorithms, like for example Shor algorithm or the Simon algorithm, and there are many others, as can be, one can check this nice review by Ashley Montanaro. So what are the features of what are the features of this paradigm? So compared to classical algorithms, we do have speed ups. So like Shor offers like exponential speed up compared to the best known classical algorithm. And then, in principle, they solve some concrete problems that are, let's say, of practical relevance. It's not extremely often, but sometimes they are. Like, as I hinted earlier, the resources needed to implement I mean, they work under the assumption that every gate is, let's say, good enough. So you do need error correction to implement them, okay? So the resource overhead is huge. And then the speed up is guaranteed only by the existing classical algorithms. So let me comment on this. So when you check this review, for example, one of the most promising algorithms at the time was the algorithm for solving linear equations, or for like, okay, it had some application in machine learning, like for recommendation systems, okay, and then people were very hopeful about it, but then I think last year, 18-year-old student of Scott Aronson, Evin Tang, sort of started to dequantize many of algorithms that have this kind of, dequantize, roughly speaking, this algorithm. And then this advantage, in some sense, is gone. So this is like some disadvantage that that the speed up is guaranteed only by the existence of classical algorithms. That is to say, if you improve classical algorithm, your speedup would be gone. Okay? Is it? Well, no. I mean, there are many people that work on classical algorithms for, So yeah, it's not unconditional. This is what I wanted to say. It's NP. Yeah. No, so this is not known what is. I will comment on this a bit later. Yeah. Yeah, so, okay, because of this, people nowadays are interested more and more in those heuristic algorithms. I see that I'm spending quite a bit of time. So basically, those algorithms, what they do, they don't require error correction. Okay, so you want to run them on those devices that are available now. You in principle can tolerate some noise, and what you roughly want to do, you want to encode some problem of your interest into optimization performed on this quantum machine. So, for example, you can encode solution of, I don't know, some NP complete problem as a ground state of some Hamiltonian, and then you are going to chill your system more and more. You want to cool it, and then you hope that if you cool it well enough, you'll be close enough to the solution. Okay. Of course, those are analog things, or sort of hybrid in some sense. So there are some other variants of this that have to do with actual implementation of gates, not only this cooling. So the good thing about this is that they tend to address practical problems. They are in principle feasible in near-term devices, but there are no guarantees of superiority of those algorithms over classical analogs, okay, over the classical counterparts. And then it is not clear how the coherence and noise affect their performance. Nevertheless, people are very much interested in them. Another thing I want to mention is quantum simulators. So many people here probably know, I mean, I don't know almost anything about quantum simulators, but basically the idea for quantum computers originated from, let's say, the dream that quantum systems in principle can simulate well other complicated quantum systems, right? So when we have, I don't know, many bosons, many fermions interacting in somehow complicated way, maybe if you can control the system quite a bit, you'll be able to simulate and understand better the behavior of real physical systems. And Manin and Feynman were the proponents of this idea. Right. So what are the features of this paradigm? So it's relevant for practical purposes. So you want to simulate complicated quantum systems. You want to maybe understand high temperature superconductivity or some phenomena from high energy physics, or or you want to understand materials. Also, they are analog, as far as I understand. Right. So the requirements are smaller, and the tricky part is that, again, you don't have, let's say, guarantee that somebody doesn't come at some point and figure out some nice, clever way, I don't know, to diagonalize the Hamiltonian to solve your system well. Okay? So this is the situation we are at. And now I turn to this quantum advantage, or quantum computational supremacy. So the idea of this scheme is to find some physical process that will not be as demanding as universal quantum computation, but it will be possible to give some complexity theoretic evidence for its difficulty from the perspective of classical computers. Okay. So what are the features? So we are going to base, let's say, this hardness of those processes on arguments outside from quantum physics. So based on complexity theory, and those proposals are in principle easier to realize in near-term devices. The downsides are like this, so still you don't understand how noise and imperfections affect them, and also they don't need to be practical, okay? So you are just going to run them as a like proof of principle that quantum devices can outperform for some task classical computers. Yeah, is it clear, roughly? Yeah, that's just okay. And basically, as far as I know, all proposals for this quantum computational advantage or supremacy, they have the following structure. So you put some standard simple input state into complicated but not too complicated circuit. So your wave function evolves, it changes, and then you measure. You get some bit string in the output, and then you sample. Yeah. So this is how those devices work. Okay. And then one can pose. One can pose the task that classical computer should do when it wants to mimic the behavior of such a quantum system. So, given a specification of the circuit, your task is to sample approximately from the probability distribution in the output from the distribution that would be close to the distribution of the quantum device. Okay? Well, the input is standard. It's like fixed. Yeah, and then you get some probability distribution. Yes. Well, okay. You can view it. You can view it as like a just classical input that would be just. Yeah. Yeah, or just all the zeros. You know. This is like the simplest part of this, okay? So when I mean sample approximately from the probability distribution that describes this quantum circuit, typically people consider so-called total variation. The classical computer would be sampling from some probability distribution p tilde c that would be close would be close in total variation distance to the quantum distribution. So it should, and importantly, it should be efficient for classical computers. So it should be like polynomial in the size of the problem. Okay, like generating a sample should take polynomial time with the number of qubits. Okay. So this is this is a very, let's say, simple to phrase task, okay? And all those quantum supremacy proposals, they have this structure, basically to mimic sampling from to reproduce sampling from the actual quantum device, okay? So it doesn't need to be practical. And let me emphasize strongly that sampling is not equivalent in any way to computing what are actually values of the probabilities, because you need to have like you need to sample many times to learn this value when you're.
So you are using disadvantage.
No. Yes, yeah, sure. So it's about sampling, okay? Yeah. Yeah, so it's true that quantum computers can be simulated on classical computers with exponential overhead. Okay, so yes, you can do it, but okay. So Adam, can you just tell me when should I finish? Half an hour. Okay. Okay. Thanks. So right. I mean, this is supposed to be physics and expository talk, so I'm not going to dwell into this, into quantum complexity theory. But let me just say that from the point of view of theoretical computer science, people associate, let's say, efficient computation with polynomial time computation, like in the size of the problem, okay? And then you have this plethora of complexity classes, both classical and quantum. So let me just briefly go with you through this, okay? So this P stands for classical polynomial time. So these are problems that can be solved in polynomial time on deterministic classical computer. Okay, so this BPP. Okay, these are just some. Okay, the names are not so important. Like it stands for probabilistic quantum classical computation. So you allow to have some random bits on your disposal, and then you maybe want to harness this randomness for your for solving your particular problem. I mean, the reason why I put here this BPP is that quantum computers, as I mentioned earlier, are inherently probabilistic. Okay, so it's not in principle fair to compare them just with polynomial computation, but classical computation, but one should compare them with polynomial probabilistic computation. Okay, so what we know, okay, is that this BQP stands basically for the power of quantum computer. Okay, so these are quantum circuits that can be efficiently implemented. Okay, and they should correspond to some solution of some problem. So specifically, you have factoring here, which is not known. It's like the reason why it is here, not here, is that people don't expect that there exists polynomial time algorithm to solve to factor numbers, even in a probabilistic fashion. On the other end, Wojtek, you mentioned this NP class. So this NP class is a class of problems that whose solution can be verified in polynomial time once you like for instance this traveling salesman problem. When you have the like the path through this graph, you can check what is its length, let's say, right? Or so you can verify. Yeah. Yes. So also factoring is also somehow in NP also here. Well, as far as okay, strictly speaking, factoring, I'm pretty sure it's in NP. It's not known if it's in BPP, but in NP it is because you can verify. What? Or? Well, okay, I'm like simplifying now because this is the class of decision problems, and factoring, strictly speaking, is not a decision problem. I mean, but you can, when you have candidates for your factors, you can verify if they. So this is. Maybe I'm missing something fundamental here. No. This is like the definition of NP class. If something is in NP. In P also, yes. So factoring might be in P, might be. Yes, might be. It is not known, but this is what, okay, it's not proven. People expect that it's not in P or not in BPP. Okay, this is, as I said, it's conditioned on the power of the best classical algorithm. But well, okay, I meant here class, not NP. Okay, I didn't want to go into those technical things. So I mean here NP, not NP complete. Okay, so so I agree with you, Eric, that if it was NP complete, it's totally not known. Okay, but then I need to explain what is NP complete, and I don't want to do it. I just mean here class of problems that can be verified, whose solution can be verified efficiently. Okay, and then you have many more classes. Yeah. Sure. Okay, so this is bounded classical probabilistic time. This is bounded quantum probabilistic time. Yeah. Okay, and then you have well, polynomial and probabilistic, I think. Yeah. Okay. The point is, you have people in complexity theory consider like many more classes built on the top of this P and P, okay? And they, for like you have zillions of classes. The point is, you can put everything inside so-called polynomial hierarchy, okay? Which still lies inside the so-called P space. This is the class of problem that can be solved in polynomial space, okay? And right, I mean, this is physics audience and it's supposed to be introductory talk. So I can just say that the idea of those quantum supremacy proposals is that there are some arguments that show that if certain classes of circuits could have been efficiently classically simulated, then that would imply the collapse of this polynomial hierarchy. So this is some hierarchy of complexity classes, and people expect it to be large and infinite in complexity theory. And existence of efficient classical algorithm would imply its collapse. So this is not a proof, but evidence. Okay. So I cannot. I'm a bit dissatisfied with the state of affairs here, of course. So this is how roughly the argumentation goes. Yes, yes. But let's say whole generations probably of computer scientists were working on, like not like they work somewhere in here for many years, you know, so their efforts will be like futile if if we manage to simulate classically those circuits. Yeah. Of course, yeah. No, you're totally right. Yeah, you're totally right. Okay, so I can now move to this proposal due to Google. Okay, so the idea is to consider a rectangular network of qubits. So here in this plane you have qubits arranged somehow on the lattice. And then you're going to apply to it, yes? Physically there would be superconducting transmon qubits.
This is what Google uses?
Yes, yes. Transmon, yes, yes. Yeah. Right, so you start. Let me before I go in details. Let me start on the logical level to describe what is going on. Okay, so you have those gates on this rectangular lattice, and then you prepare a random. You prepare a random quantum circuit. So you choose your gates at random in some fashion. Okay, from this gate set. So this is specific gate set that they consider. Don't ask me at the moment why they consider this. So this is like square root of Pauli x, square root of Pauli y on the single qubit, square root of such like superposition x plus y, okay? And then some entangling gate. These are gates that affect individual qubits. This is some entangling gate. So you put those gates in some according to some pattern in this network.
Is anybody hopeful that this will produce something useful?
I will comment on this maybe later. Okay, if you yes, and then as I was explaining earlier, so this is I'm not talking about my results. I'm just referring to what people are doing in the field. So. So in the end, you measure, as I was explaining, qubits in the output of the circuit. Yeah. Okay, I said it's I swap. I was surprised. So this I swap apparently it's like the following gate, if you want. I had to Google it. It's something like it's this. This is swap. This maybe you guys know V. You call it V typically, right? So this is what they mean by. I think it's something like this. Hopefully, I didn't. I hope it's unitary. Actually, yeah. So I's in this. Yeah, I don't know why they chose it. Yes.
So physically, you've got this circuits with
Yeah.
just transactions.
Yes.
But all these operations are implemented physically by doing what?
So I think I'm not an expert on this, but they are controlled by like silent microwave pulses. Yes. But let me. I will. There will be more details later. Okay. So, and then the point is, okay, you are measuring. Look, guys, this is actually this Google proposal. So bear with me. Okay. So you have. This device samples according to this probability distribution, and then if your circuit is deep enough, the intuition is that you will be exploring the unitary group so somehow evenly. Okay, so for experts it will be some kind of like T design or yeah. So I said it will be some kind of a T design. Well, then it's not extremely important. It's just evenly in a sense that you can imagine the space of unitaries, okay, and you'll be like spreading over it like in somehow uniform manner.
In physical terms, what is the interaction between the levels of this system?
Well, okay, so right. So I must say I'm not an expert on this. So I think there are you control also by hardware properties of those qubits individually, and also some elements that sit in between. And then on the top of this, you send those microwave pulses, and effectively you. Okay, simply it's yeah. No. I think it's not, but sort of it's yeah. Yes. So actually, the guy who is responsible for this, John Martinez, from University Santa Barbara, he is like the leader of developing those superconducting qubits. Okay, and that's why Google hired him a while ago, just to build these devices for it. So it's open enough, I think, for yeah. Okay, so the layout that I consider is motivated by, let's say, proposals for quantum error correction for some things like surface code. The theoretical proposal was put forward by Google team in 2016. But some more rigorous complexity theoretic justifications came only later, like in 2016 and 18, but it's published this year actually. So now I can go to the paper. Okay, I must confess I was like overwhelmed by the paper, even though I work in the field. I gave myself roughly 5 days maybe to understand it. It was overwhelming. So I'm just because it's like 5-6 pages, but then it has 60 pages of appendix, okay? So it's like a thick piece. So I'm just going to give you account for how much I understood roughly from it. So just some comment. So the field starts to be a bit like high energy physics, in my opinion, because it's over 70 authors. So it's really like a massive effort of many people, both theorists and experimentalists, which I think is nice. And these are there are zillions of people involved in this, but I mentioned already John Martinez, who is the professor in this University of Santa Barbara, and Sergio Boisho, hired by Google now. So he's a theorist that put forward this proposal, let's say. And right, so I'll be going step by step, quickly enough, let's say, over some passages from their abstract. Okay, so first thing, okay, they motivate why they are doing what they are doing, but then they go and say that they have this very large superconducting quantum processor. Okay, yeah, that affects that explores huge state space. Right, and on the physics side, I mean, it's very profound and deep physics, which I must confess I'm a like mathematical physicist. I don't understand the details, but they are able to put to manufacture and put together many qubits. Okay, these are like superconducting. 53. Okay, so it's like 54, but this one was malfunctioning. Okay, for some days. Yeah, and then this is what I said. So they had some circuit in between that sort of can turn off the interaction between this, between the neighboring qubits. Okay, and the control is okay via those microwave pulses. Actually, I'm not going to lie to you. I'm not an expert on those things, although I'd like to understand more. Yeah.
One crucial question.
Yeah.
Have you been able to dig out how many out of 53 qubits they can control?
Yeah, so I'm going to there. Yes, yes. So, right, exactly. So it's, in my view, kind of nice, very nice achievement, because for the first time, people were able to put together so many qubits and test and benchmark them. This exactly answers your question, Jarek, right? So this plot. So here they were doing, let's say, error analysis for single qubit gates, 2 qubit gates, okay, and also measurements. Okay, so here you have this layout, and okay, colors indicate what are the errors, roughly speaking. Okay, and importantly, they were doing it individually, so they were either like turning off this interaction completely, and they were assessing the quality of qubits, but also they were assessing them when they were all talking to each other. Okay, and the results are quite beautiful. So they are given by this histogram here. So right here you have like the rate of the error. Okay, and let's say here are like single qubit errors. So it tells you like how many, let's say, how many qubits have errors smaller than let's say this like I don't know 10 like 1% or 1/10 of the percent. Okay, so.
What's the percentage of the error of one qubit?
No. So for one, what? No. Sure, that's no. Okay, so you can treat those things, let's say, as like those gates as channels, and you can do in principle their tomography. Okay, and you can check so-called fidelity between fidelity. Okay, they don't do exactly this, but something close. So this is simplified. This is simplified figure of merit, but still, yeah. No. So I'm going to address this a bit in a second. So they considered 1 and 2 qubit only at this moment. Okay. So okay, and then isolated errors are for single qubits are quite small, so like 1/10 of the percent. But for 2 qubit errors, they can go up to 1%. I want to point to your attention that errors when you have readout, okay, so readout errors are kind of easy to understand because they correspond to misreading the result. So it should be 1, but you got 0 or the other way around. So they're like 4%. Okay, so they did this exhaustive, let's say, tomography or benchmarking of the device, which is pretty impressive. Right, and then Okay, then they say that measurements conducted on this device were, okay, they conducted the experiments and they verified them using classical simulations. Okay, so this is the tricky part. Right, so when you have larger and larger quantum states, it becomes unfeasible to do tomography of them because they are exponentially complex. Okay, so you cannot, you need to repeat something exponential many times. So they came up with some kind of a benchmark, so-called linear cross-entropy benchmark, which is a function of the circuit and the samples that you observe. So those x1 up to xk's are the samples that you observe. You run your circuit k times. So this is a normalization, but here you need to compute, this is important, the probability of getting this particular outcome, and then you average over all outcomes that you, let's say, observed. So if you observed, let's say, 2 times some particular outcome, you need to count this probability twice. If on the other end, particular outcome was not observed, it wouldn't appear in this expression. Okay, so this is just empirical average. And then, based on some random matrix theory arguments like designs and stuff, one can argue that this cross entropy, this fidelity, should be 1 in the ideal case. I'm just conveying in a very simplified fashion what they are saying, okay? And then they introduce. So this is if this entropy is like 1, this is supposed to be good, okay? And now they have phenomenological error model, which is actually pretty simple. So they like the actual state that comes out from this device is just some tiny bit of the actual true state that was supposed to be implemented, plus white noise. Okay, and then the magnitude of this true state depends on how many single qubit gates you had, how many 2-qubit gates you had. So this is very simplified model. You just treat it purely classically. Okay. Then when you so this E1 and E2 stand for single qubit errors and 2-qubit errors. Now, when you now compute this for this error model, this cross entropy, it decays according to this prescription. This is what they, let's say, what they argue, and they test it numerically. 5 minutes. Okay, I will, yeah. Right, so some things I will skip then. No, but this is actually, those 2 plots are the things that sort of make them claim the quantum supremacy or advantage, okay? So here is what they do. Okay, it's not so easy, so bear with me. So they are running those circuits, okay, for different number of qubits and different depths, and they run them and they compute this cross entropy, okay. And let's say this red is the actual true circuit that they want to implement. So this is the number that they got experimentally, okay. Whereas the black curve corresponds to this theoretical prediction. So this is how they test. It refers to your question. Yeah, it's some kind of benchmarking. So they benchmark that the error that they postulated is in some sense valid. So this fidelity decays like this with, yeah.
What I was trying to ask is how many qubits they can control, they can prepare in, let's say, multi-qubit.
Well, so 53.
I don't think so, because
Yeah.
recent estimates were 18, maybe 20 qubits.
Well, I'm just saying what they claim, right? And they did benchmarking of this integrated device, right? And also, I mean, this is actually the data from their device. Okay, so they had this model of error of imperfections, and for this particular figure of merit, it seems to, let's say, agree. This is not more than this. This is benchmarking.
Yes, exactly. So it does not. They can have a circuit which does not need, let's say, 50 qubit entanglement. They can have a circuit which needs only 10 qubits.
Sure. But that's true.
I was
Yeah.
just curious if they manage to push the current limit of coherent control, which is around 20 qubits.
So depends how you view it, I would say. Yes.
They say 53, IBM claims they have 52, so that's
Right. Okay. Okay. So let me. Okay. Can I just? I will try to convey where they claim the supremacy. Okay. So important part is that when you compute this fidelity, you need to compute those probabilities, which is hard. Okay. So for some simple circuits, okay, when your number of qubits is not too large, you can compute it. Okay. But now, when you have greater number of qubits, which is described here, this 53 qubits, you can compute those numbers. Only for simplified circuits, so they simplified the layout a bit, and they can classically simulate what's going on. And they observe, I'm just quoting them, right? So they observe that this model, let's say, agrees. And now, this is what they claim. So they cannot compute those numbers anymore due to computational limitations for the actual circuit, okay? And so they claim that this fidelity would be large enough, would be comparable to this, okay? To what they observed for simpler circuits. So this is some kind of shaky part, but they make this, it's like engineering guess, but they make such a guess, okay? And then, okay, so this is some benchmark for them. Why that tells like what is the fidelity of the gates, fidelity of the state, even after the complicated circuit. And then I must say, okay, there is this passage from the abstract that was the reason why then IBM attacked them so much. So they can for this depth like 20 and 53 qubits, then they sample like millions of samples like in 200 seconds, and they estimate that the runtime is 10,000 years. I don't have time to, like the classical time would be 10,000 years to repeat this task. Okay, actually it's like the most difficult part of the paper. Okay, I don't have. What I should say. So basically, I have some slides prepared about it. But basically, the core of this controversy is that they used very specific algorithm to compute amplitudes of this quantum circuit. That they needed to, let's say, that they needed to verify the circuit, and this algorithm was trading space for time. So you'd be like, you typically put your when you compute, you put stuff in RAM. You don't use hard drive very much, and they use some. Okay, so they didn't want so RAM, when you want to run fast, goes out quickly. So they said that it's impossible to go on with certain algorithm because memory would be like would have to be too large. So IBM went, let's say, roughly speaking, to simplified to different method that relies on hard drive. But there is like, believe me, there are like a couple of like technical 30 pages paper that describes how you take how you take into account that you have different cores, you have to schedule the thing. It's very complicated, but this is the basic idea. Okay, there is some nice about those simulations. There are some nice things related to path integrals, but I don't have time to talk about them. Just maybe one things. So there are some more, even on the theoretical side, more caveats that one should address. First of all, there is, let's say, no-go theorem for certification of quantum advantage. Okay, so people from Berlin last year proved that due to properties of the probability distributions that you get in those random circuits, you won't be able to certify in a somehow rigorous way that your device is actually performing well. So that's why you see they had to do some tricks, okay? So you need to sample this thing exponentially many times to verify under the current state of the art, okay? Another thing that I want to maybe point out is that those circuits are noisy and imperfect, and it makes sense to take advantage of this noisiness to come up with new classical simulation methods that use it. Okay, some advertisement, I did it with my colleague for this paradigm of boson sampling, but it would be interesting to do it also for these more complicated systems. That's really the summary. Okay, so this quantum computational advantage is still a very attractive milestone in the field of quantum computation, and I think that Google and people from Santa Barbara and NASA made very nice progress in manufacturing complicated and controllable, programmable quantum processor, but at the same time, you know, they are racing, or we are racing with increasing capabilities of classical computers, classical algorithms, okay? And it's therefore still a lot of work has to be done, both on the experimental and theoretical side in this field. So I'm like very excited to work in it. Yeah, thank you. These are the things that I want to do in the future. Yeah.
Okay, any questions, comments?
This is going to be a silly question because I'm not expert, but the main message I took from your talk is that they prove quantum supremacy in the device that is quantum CPU that could produce numbers like fidelity, which are also related to simulating quantum devices. So
yes.
There's not single practical algorithm application here. So isn't it surprising that quantum computer is better at simulating quantum computer than classical computer? To some
is
extent,
it surprising that quantum
computer is better at simulating or verifying quantum system than the classical computer?
No, I think this is not
Surprising, yes.
I should maybe comment that there is one proposal, but one of the researchers, Scott Aronson, to take the average actually from this, let's say, randomness generated in those circuits and generate randomness analogously to what people do in Bell tests. But I didn't go through the details of this.
More questions?
I'm afraid I still don't understand the difference between my smartphone and the quantum computer. It is obvious that to simulate what happens in this device by classical computer would be hopeless. However, if I put some input and I get the output, that mechanism is quantum mechanical. So why this is not a model of a quantum computer? Where is the essential difference?
Wait, I mean the input and output are classical, but inside you have in principle processing information quantum.
No, I have quantum device here because at the very basic level,
sure.
Quantum.
Yeah.
How do? Wait, I control this using classical concepts, and that is also true for this quantum computer because the input is certainly classical. Microwaves are controlled by quantum.
Yeah, input is classical, but processing in principle is not.
Which processing?
Like inside, like when you, okay, it's very, like I don't know, like inside here when you have this, like here you have input, you can also have classical control that tells you what gates you're going to do, but inside is quantum and you cannot keep track of it. Of course you can keep track easily what goes out. Yeah. I mean, so here in those, of course.
But the superposition, at the very beginning, superposition is induced by a classical device.
Yes.
The generator of microwaves.
Yes.
One more question.
I would say, I think that the difference is that you can do something which is called massive parallel. In that respect, that you put some input state, but you can go simultaneously through all possibilities and then project some output state. But that's something which is much faster. Classical computer will do it sequentially, one after another, because we don't have infinite number of processors. In that respect, quantum computer, it induces massive parallel part, and that's why short algorithm is faster than anything else, except for one fact, which I just would like to remind you. It is known that factorization breaks RSA, but it is not known whether there is another attack on RSA which does not require factorization.
Which simply factorize the numbers.
Yes, but maybe RSA can be broken in different way, and the complexity
okay,
of...
Let's not talk about RSA, but of factorizing numbers. But
Nothing is known about it.
But it's also not known that there is some. But the problem is here that you have this here for, not for a... Okay.
Any questions to the speaker? If not, let's thank Michał once again.